In this video, we are going to look at how the formula for a sinusoidal function is related to the graph's amplitude, period, and midline. Ultimately, the goal is to be able to take a real-world wave pattern, write down the amplitude, write down the period, and write down the midline based on a chart for that wave. And then to construct a sinusoidal function that matches the real-world wave in those three features. So today is part 2. How do you construct a sinusoidal function that has a specified amplitude, period, and midline? So we're going to approach this in a sort of exploratory way. I'm not going to come right out immediately and tell you the rule, because if you learn the rule without knowing why the rule really works, it can be hard to remember. So let's begin with some exploration. Let's go to Desmos and let's compare the sinusoidal function 3 times sine of t with the function regular sine of t. And let's figure out how multiplying the function by 3 will affect its amplitude, its period, and or its midline. Now, looking at these two graphs, the midline has not changed at all. Both functions have a midline of y equals 0. The x-axis cuts directly in between both of these two waves. Additionally, the period has not changed at all. If I look at the distance between peaks, for example, in both cases, the peaks are 2 pi units apart. So multiplying the function by 3 has not changed the period or the midline. However, multiplying the function by 3 has most certainly changed the amplitude. Under normal circumstances, the amplitude of the regular sine function is positive 1, because it takes 1 unit to travel from the midline to the peak. But by multiplying by 3, our amplitude has also been tripled. By multiplying by 3, now it takes us 3 units of distance to travel from midline to peak. Now, as a quick note, we have a positive 3 here. But if we happen to put a negative 3 here, it will flip the graph vertically, but the amplitude will not actually change. The amplitude of negative 3 sine x is the same. It would take 3 units of distance to go from the midline at y equals 0 up to the peak at y equals 3. So to sum up our observations, amplitude of 3 sine t is 3 units, and the period and the midline were unaffected. Having made these observations, let's go ahead and write down the following rule. What I'll write down is that the amplitude of number multiplied by sine t is the absolute value of that multiplied number. Absolute value because, for example, whether we multiplied sine by positive 3 or by negative 3, the amplitude was still equal to positive 3. It took 3 units to get from the midline to the peak. Another way to phrase this same rule that might be a little bit more useful is to say that if you want a sine function, if you want a wave with an amplitude of, let's say, a, and then you can achieve that by multiplying the regular ordinary sine function by the desired amplitude a. For example, someone says to me, I would like to construct a wave with an amplitude of 7 units. The easiest way to achieve that is just to stick a multiplied 7 on the outside of sine and that will give you a wave with an amplitude of 7 units. When you think back to transformations, this does make sense. When we studied transformations, we learned that when we multiply a function by a number, then this causes the graph to be stretched by a factor that was equal to this number. So as an exercise, someone gives me a function f of t is equal to the number negative 0.1 times sine of t, and they say, what's the amplitude of this function? To find the amplitude of this function, all I have to do is look at the multiplied number in front of sine, take its absolute value to make it positive, because amplitude is a distance and distances are always positive, and that'll be my amplitude. So they'll take the absolute value of 0.1, and the result will be 0.1 positive, and that is the amplitude. So next up, let's see if we can figure out what feature of the graph will affect not the amplitude, but the period instead. And inspired by that exercise at the end of yesterday's video, I'm going to see what happens if I multiply not the outside of sine, but multiply the input of sine by some number. Now, as a result of that, I have achieved the blue graph, which is oscillating between max and min faster than sine did. The function sine of 2x is running at double speed compared to sine of regular x. And so it takes half as much time for the graph to complete one cycle. Instead of a period of 2 pi, the graph of sine of 2x has its period cut in half. Now the period is only pi units. So the period is affected by multiplying the input by a number. Notice, however, that the midline and the amplitude are completely unaffected. For both the red graph and the blue graph, the midline is still here at y equals 0. For both the red graph and the blue graph, there's 1 unit of vertical distance between the midline and the peak. So multiplying the input affects the period, but doesn't affect the amplitude in the midline at all. For sine of 2x, period was half as long. But in this case, the midline and the amplitude were unaffected. So here's the rule that applies for trying to get a sinusoidal function of a specific period. The rule is that the period of the function sine with a number like b plugged into the input multiplied by t can be found by taking 2 pi and dividing it by b. Now let's try and rephrase this rule so that I could use it to construct a sine function with a specific period. We know that the period can be found by taking 2 pi and dividing it by b. So now if I clear these two fractions, period multiplied by b is equal to 2 pi, and isolate b by dividing out the period, what this is telling me is that if I want to construct a sine function with a specific period, let's call it P for short, write down the number 2 pi divided by the period and use the sine function where the input is multiplied by that quantity. For example, suppose you're trying to construct a sinusoidal function which matches a wave pattern that repeats once per day. So you want to construct a function where the period is equal to 1 day. In this case, you would set b equal to 2 pi divided by this period, which is equal to 1. 2 pi divided by 1 would just be 2 pi. So if you wanted the wave to repeat every single day, once per day, the sine function that you would use is sine of b, sine of 2 pi, multiplied by the input. This sine function would have a period of 1 unit. Returning to Desmos, we can confirm this fact. I want a sine function with a period of 1 unit, and we found that to achieve that, we can multiply the input by the number 2 pi. If I graph that function, you can confirm that this particular function, its wave pattern repeats every 1 unit. There is 1 unit between the two peaks, or there is 1 unit between the beginning of one cycle and the beginning of the next cycle. 2 pi in the input would give you a period of 1. Now, if we go back to thinking about transformations as we learned them in Pre-Calculus 1, this does make some sense. In Pre-Calculus 1, we learned that if we multiply the input by a number, such as b, this created a horizontal stretch or compression by a factor of 1 over b. For example, if you put a 2 in the input, the graph is going to be half of its normal size. So if I put a b in the input, the period is going to get divided by b, the same way that the period was cut in half when we had a 2 in the input. As an exercise, someone says, let me look at the sinusoidal function sine of a single pi multiplied by t. If b is pi, what's the period? So the relationship between the period and b is that the period is equal to 2 pi divided by the b value, which in this particular problem is given as pi. So this particular wave would repeat every 2 units. Let's figure out what feature of the function influences the graph's midline. Now, I remember from the exercise at the end of yesterday that there seemed to be a relationship between the midline and the number that was being added or subtracted to the output of sine. So let's have a look at what happens when you take sine of t and add a number to it, for example, add 5. So adding 5 to the sine function has finally changed the midline. The regular sine function, graphed in red, has its normal midline at y equals 0. However, once I added 5 to the output of sine was vertically shifted upward by 5 units, and that vertical shift of the sine function carried the midline up as well. So the midline of sine of x plus 5 is up here at y equals 5 now. What we found is that the midline of the sine of t plus 5 is at y equals 5. But the period and the amplitude in this case are not affected. Let's go back to that Desmos picture for just a second. Both the red sine and the green shifted sine repeat every 2 pi units, so the speed of the cycle has not changed at all. Additionally, the amplitude has not changed. Here, for the red original sine, the amplitude is of course 1 unit to get from y equals 0 up to y equals 1. But for the green sine function, the amplitude is still 1 unit. This time, 1 unit is what is needed to take us from the midline at 5 to the peak at y equals 6. The rule is that the midline of sine of t plus some number, let's call it c, is at y equals c. Or, as is sometimes more useful, the rephrase of this rule would be, if you want a wave, with a midline at y equals c, all you have to do is take your original sine function and add a c to it. In the language of Pre-Calculus 1 and the transformations that were studied in this course, this does make some sense because adding c to the output of a function is a vertical shift up/down by c units. Up if c is actually a positive number, and down if c was a negative number. And when you shift the sine function vertically up or down, the midline also gets shifted up or down by the same amount. To quickly use this property, someone says, what is the midline of f of t is equal to sine of t minus 4. This person has added a negative 4 to their sine function, so the midline has been shifted 4 units down as the entire function has been shifted 4 units down. So to summarize, if someone gives you a sinusoidal function of the most general format, what is the function's amplitude, period, and midline? The amplitude is the absolute value of whatever number is outside here of sine. The period can be obtained by taking the normal period of the regular sine function and dividing it by the b in the parentheses. And the midline is a match to whatever number is being added or subtracted in the output. Another way to put this exact same result is that if you want a sinusoidal function with a specific amplitude, a specific period, and a specific midline, then use the function where you take the amplitude and you multiply it on the outside by sine, then take the number 2 pi divided by the period and multiply that on the inside by your input, and then on the outside of sine, add the value of the midline. Now, there's one variety of transformation that we really haven't talked about so far, and that is the horizontal shift. But horizontal shifts will not affect the amplitude, the period, or the midline. For example here, exercise. Let's identify the period, amplitude, and midline of the following function and quickly sketch a graph of this function. So the amplitude would be equal to the absolute value of this number out in front multiplied by sine on the outside. Of course, the number is already positive, so we don't need to apply the absolute value to make it positive so that it makes sense as an actual distance. The amplitude is just equal to the number positive 2. What about the midline? The midline is given by this added number added here in the back. So the midline would be located at the level y equals 1. This is going to be the average value directly in the middle of the wave. What about the period? How long will it take for this graph to repeat itself? Well, the multiplied 3 in the input is a sign that the function is executing its behavior 3 times faster than the normal sine function. So it will only take 1/3 the normal amount of time for the function to repeat. 2 pi divided by 3 is the period. So let's confirm our results by looking at a quick graph of this function. So we have a wave pattern with a minimum value of -1 and a maximum value of +3. And directly in between the minimum and maximum is the midline located at y equals +1 as expected. The distance between the midline at y equals +1 and the peak at +3 is 2 units as expected. And looking at the graph and looking at the horizontal distance between two subsequent peaks, it takes exactly 2 pi over 3 horizontal units to get from one peak to the next. So the period is exactly what we wanted. To conclude with one final exercise, let's try and come up with a formula for a sinusoidal function that matches this wave pattern that we saw with this concurrent steam users chart. The midline was over here at approximately 14 million users. The distance between midline and peak corresponded to approximately 3 million users. The distance between peaks, horizontal distance between peaks, or time between peaks, was 1 day. So using the formula above, I'll construct the following sine function. I will multiply the output by 3 million. In the parentheses, I will multiply the input by 2 pi divided by the period. And I will add the midline of 14 million to sine on the outside. And this function, when graphed on the same scale as this chart, will match the chart as well as anything mathematical can match anything real. That concludes today's material. Today we studied how to construct a sinusoidal function with a specific amplitude, period, and midline. The amplitude was controlled by a multiplied number in front, the midline was controlled by an added number in back, and the period was controlled by a number that was multiplied by the input inside the sine function.